There's this growing community of developer conferences about functional programming. It's an amazing thing. Lambda Days is one of the groups that's been leading the way, and the size of the audience has been steadily growing. So that wow was very heartfelt, and I want you to give yourselves a round of applause for leading in this growing community. So I'm going to be talking about something near and dear to my heart, category theory. Everybody keeps getting upset that some of us talk about mathematics. Some of you get excited, which is great, but some of you get upset. And that's very sad, right? There's a 17th century mathematician who said, if you can solve a problem and use mathematics to do it, and do not use mathematics, it's as if you are looking for something in the dark and refuse to light a candle. This is what mathematics is. It is your candle for seeing your way. And some people think, oh, no, I can't do mathematics. It's too hard. No, what's hard is not using the mathematics when you can. You can all learn and use the relevant mathematics. So if you get nothing else out of today, I hope what you get out of it is mathematics is your friend. Okay? And I'm almost going to run down and get my little fluffy Lambda out of the bag, but I won't. I have a little no, I will. See, mathematics is fluffy. It's your friend. It's cuddly. It's warm. It's a Smuffy. My daughter made this for me. My daughter has lots of little cuddly toys, which are called Smuffies. Well, she's grown up now. Now she has a kitten instead. But she made this for me because she thought that I should have something warm and cuddly. And I think it best indicates the attitude you should take towards mathematics. So how many of you think mathematics is your friend? Good. How many are kind of scared of it because they think it's not for them? Okay. Of those of you guys who think it's not for them, how many of you know JavaScript? Right. JavaScript is much, much harder than mathematics. Right? Mathematics is designed to be understood and sensible and consistent. So don't panic, right? When you see mathematics, don't panic. You can do it. It's your friend. It's fun. It is fun. It's exciting. It's, this is what got me excited when I first entered functional programming. The idea that people had designed instruction sets for machines back in the 1930s, before we started building stored program computers. So, functional programming is just a little bit older than the stored program computer, right? And we all talk about Turing as one of the founders of our field, right? And Turing went to study with Alonzo Church. And indeed, Turing wrote the paper proving that lambda calculus and Turing machines were equivalent. At the very beginning of it, he says, and this means we can use the more elegant lambda expressions. So it goes back a real long way, just slightly further than the beginning of computing. And it's great. So let me tell you a little bit about category theory. Category theory is often the secret sauce behind things. So like people get scared of the name monad in Haskell, and it comes from category theory. But the whole point is you don't need to know any category theory at all to use monads. If you know category theory, then it can help you discover things like monads. That's what it's there for, to help you discover it. What I've often thought, and you'll see here, right? What category theory really is stuff that's really familiar and that you know really well, made difficult. And then you might think, well, why do I want to make it difficult? But by stripping stuff away, you get at the essence of things, and you can see things that you wouldn't see otherwise. So I'll show you a little bit about that. I'm just going to show you just enough category theory for the very basic data structures that we use in computing. And it's precisely because of learning this category theory that drove home to me why these are the basic data structures. Right? You might think about some other stuff, like the array. No, it's not the array. Okay? The three basic structures that you need are the product, the sum, and the exponential. So let's learn about those. And then sort of a boost to giving this talk is that recently there have been a lot of scripting languages for smart contracts coming along, and lots of people doing this are very clever. So there are things like Simplicity and Michelson and Plutus, which is done by IOHK, a company I consult for. And the category theory isn't hidden anymore. It's right out in front. You can see that they're making use of these ideas in ways that were previously behind the scenes, are now right up front. So I find that quite exciting. And that's great for motivating stuff, right? Cryptocurrency. What could be cooler than that? And they're making use of these ideas. So let me show you what a category is. It's very simple. You write some stuff in blue and some in red and some in black. Wait, no, don't do that. Go back. Why doesn't it like me? That's what doesn't like me. Okay, there we go. So you write some stuff in blue, right here. Thingies in blue are called objects. Just a new name for a thingy. Thingies in black are called arrows, and I'll write their names in red, and that's it. So one model of this that you might think of is set theory, and you can think of A as a set, and B as a set, and then F is a function whose domain is A and whose range is B. That's one way you could think of it. Another way you could think of it, if you know any algebra, is that A is an algebra, and B is an algebra, and F is a morphism between algebras, or a homomorphism, and that means it preserves the algebraic structure. So if A has some operator on it, and X and Y are two elements of A, then we can either combine X and Y with the operator and then do F to the result, or we can do F to the X and F to the Y, and that'll move them both into B, and then in B we can use B's operator, and that'll give us the same thing. So this notion that you can just, things are preserved by functions is called a homomorphism. That's a big name for a very simple idea. And then there are other structures that map onto these as well. This might be a type in a programming language, and this might be a function that, given a value of this type, computes a value of this type. Or you might be in logic, and this is a formula, and this is a formula, and this is a proof that this formula implies this formula. So there are lots of different ways of viewing this. But if you're confused by that, just think sets and functions. That would be fine. Okay, and then we're given very little structure about these arrows, but we're given a bit of structure. We're told two things. Well, first of all, if F is an arrow from A to B, and B is an arrow from G to C, then F semicolon G, F followed by G, sometimes also written G circle F, just if you like doing everything backwards. F circle G, of course, would be an arrow from A to C. So we call that composition of functions, which is mathematics for sticking a couple of functions together. And the other one thing we have is that for each object, such as A, there's an arrow, identity of A, that goes from it back to itself and does nothing, right? One of the functions that exist is the function that does nothing. And we're told a little bit about these. Oh, right, they're called objects and arrows. I told you that. Right, and then we know a little bit about these things. We know that composition is dissociative, meaning if you stick F and G together and then stick that together with H, that's the same as sticking F together with G and H stuck together. Okay, so the order of parentheses doesn't matter. And if you do the identity and follow it by F, well, that's of course just the same as F, and that's the same as F followed by the identity on B, since B is the range of F. Okay, and these objects, this object is sometimes called the source of F, and this is called the target of F. But it's the same as domain and range. Are there any questions? No, you're all being shy. Okay, here is how you learn stuff. Don't be shy. If you have a question, ask a question. I will consider this talk successful if I get some questions during the talk. So I hope you'll help me make this a successful talk. Are there any questions? Yes. So does this imply does it have to be a homomorphism? So there are different ways you can interpret objects and arrows. You can just set down the rules, and you can say every object is a set. Every arrow is a function from the range set to the domain set. Or you can let down a different set of rules, and you can say every object is an algebra, and every arrow stands for a homomorphism between the algebras. So you just pick your rules. And one way of picking the rules, which is common, is to have algebras and homomorphisms. Does that answer your question? Okay, good question. Thank you. Any other? Yes. Oh, can A, B, and C be anything? Generally, again, you just set the rules and you say, this is my collection of objects. I would have said set of objects, but maybe my objects are sets, and then you need something different for a set of sets. Bits of mathematics I won't get into because infinity can be hard. But we don't need that. So you just say, these are the things that may be objects. And a typical thing to say is it could be any set whatsoever. Okay, and then there will only be certain functions available between these things, right? So the one constraint is that this must be an F that's compatible with A and B, right? So that is a very important constraint. That's actually a whole type system. So we're already away from any dynamically typed language, right? So category theory has the types built in. Indeed, one way to think of A and B is as types, and then F is a function that takes something of this type and returns something of that type. Also a good question. Okay, shall I move? Let's move on. I don't want to take ages over this. Okay, you now know enough category theory. Actually, no, I'm going to show you one more thing. You already have there enough structure to do one of the most important things, which is I can say, I should have drawn a picture of this, sorry. But you say you've got A and B, and let's say we've got F as an arrow from A to B, and G is an arrow from B back to A. Right, so here G is drawn as an arrow from B to C, but let's say G goes from B back to A. And let's say that I say, and the composition of these two things, either way gives you the identity. So F followed by G is the identity on A, G followed by F, right, G followed by F would be the identity on B. So you can already describe that amount of structure. How many people know what that thing is called? If you've got such an F and a G? Ooh, very few of you. Great. Okay, I get to tell the rest of you what's called. It's called, big name, an isomorphism. Okay. So that's great. You now know one big word, isomorphism, but it just means, oh, I've got a pair of functions going back and forth that composed are the identity. In other words, this thing and this thing are in one-to-one correspondence. So how many people have heard of one-to-one correspondence back in high school when you had functions? Okay. At least half of you are willing to admit to it. The other half of you heard about it but are shy about raising your hands. So just the notion of things being in one-to-one correspondence, that you can map back and forth either way, and that if you go a round trip, you end up where you started with. That's just two things in very close correspondence, and that's called an isomorphism. Okay, we'll make use of that in what follows. So already, even though we have a very tiny amount of structure here, right? Just function composition and identity, and that's it. That's already enough to do quite a lot. So let me show you all the things you can build. particular, we can build up the three things we want: products, sums, and exponentials, just from this amount of structure. Do you want to see that? It's cool. Okay, so we'll start with the product. So here's a little diagram. So I've got some objects, A, B, and C, and I've got another object whose name is A times B, the product of A and B. And the product has to satisfy some properties. In fact, it satisfies what's called a universal property. And all that means is that we're just saying for any object C, let's say that from C I've got an arrow from C to A, call it F. And say I've got an arrow from C to B, call it G. Now also, the product comes equipped with arrows. So from A times B, there's an arrow called first going to A, and an arrow called second going to B. So I should have started with that. So the product, objects A and B, a new object, A times B, with arrows, first going from A times B to A, and second going from A times B to B, and a universal property, which tells us for any object C. So this is specific A and B that give us A times B. And then for any C whatsoever, given an F going from C to A and a G going from C to B, there exists a unique arrow called open angle F, comma, close angle. Sorry, open angle FG. F comma G, close angle, here it is, that goes from C to A times B. And it's not just for any, and then the property of this FG is not just that it goes to A times B, but that this diagram commutes. So you can see there are two ways to get from C to A. I can go directly via F, or I can go via this FG thingy to A times B, and then via first to A, right? So I can go this way, or I can go that way. And it's called a commuting diagram, not because it gets you stuck in traffic in the morning, but because no matter which way you go around it, you get the same thing. So this is telling us that F is equal to FG followed by first, and similarly that G is equal to FG followed by second. And I think, right, and there's those two equations. FG followed by first is F, FG followed by second, oh, don't do that, go back. FG followed by second is G. Any questions about that? Yes? Is the angle brackets the same as? Oh, you're a computer scientist, you understand this. We use different symbols for different functions. So traditionally, this is just written as angle brackets. Indeed, they must match the same way parentheses match. And it's just a way of saying, okay, I'm just combining F and G to form a product. Okay, later we'll see something with different shaped brackets. So it's just a way of saying which function this is. So the thing inside angle brackets is just the thingy that goes from C to A times B. It's the thing that creates a product, or the morphism into the product. The uniquely existent morphism into the product that you know exists uniquely whenever you have an F and a G. If there's another question? Yes. Yes. Speak up. Oh, that's fine. Okay, so the question was, you're given A and B and A times B in first and second. So that's what it means to provide a product. And then there's one more, so the recipe sort of says, well, are there any products around here? Let me see. So the product of A and B will be this thing called A times B. It must have an arrow first going into A, an arrow second going into B. all that's just for a given A and B. And then we say, for any C whatsoever, for any F from C to A, for any G from C to B, there must exist a unique FG going from C to A times B such that this diagram commutes. So FG followed by first must be F, FG followed by second must be G. And then your question was, what if there is no such C? That's fine. We said, for all C, this must commute. For all C, for all F, for all G, this must commute. What if there is no C, F, or G? Fine, it's immediately a product. So then you say, oh, right, so that must mean in a discrete category, when with no arrows whatsoever, everything is a product. But not quite, because to have the product, we need to have an arrow first and we need to have an arrow second. So in a discrete category, these wouldn't exist. Right? So there will always be at least one choice for C, right? Because we should always be able to choose C to be A times B, and we could choose F to be first, and we could choose G to be second. And then first angle bracket second must be the identity because it's the unique thing. In fact, I'll show you that on a slide in a minute. So there's always at least one. Yes? Right, what we're told not only is that this exists, but it's unique. What does unique mean? That's a very good question. Here's what unique means. Let's say we've got some other H, and that H also satisfies that H followed by first is F, and H followed by second is G. And the H goes from C to A times B. So here we've got that. Then what do we know? Since it's unique and H satisfies the same properties as FG, H and FG must be the same thing. So the answer is H and FG must be equal. Now, if you were Bill Clinton, you would say, but what does equals mean? But we won't get into that. Does that answer your question? Okay, good. Excellent questions. Does anybody want to ask a question that will take me to my next slide? Now, have you worked out yet what the product is in terms of stuff that you know? How many people understand what the product is? Probably mysterious. Oh, most of you have worked it out. That's cool. Okay, so what the product is, in set theory, this is what's called the Cartesian product. In computing, this is called a record with two fields, called first and second. So at first, the arrow here just extracts the value of the first component of the pair. This is the pair type. That's another way of saying it. So, and what do we do? Well, C, if applying F takes a C to an A, applying G takes a C to a B, the way we get an A-B pair is we apply F, and that's the first component of the pair, and we apply G, and that's the second component of the pair. So it's just, this FG is just a pair builder. That's one level up, right? It's at the function level. It says for a given C, apply F to get an A, and apply G to get a B. That's a pair of things, so FG returns that pair of things. Is that clear enough? Okay, I'll show it to you in Java and in Haskell in a minute. But notice, right, somebody asked about uniqueness. Can we do anything there? Yes, we can. We can prove things like the following. So we already have enough to prove some stuff. You can prove, So remember, this works for any F and G. I can pick F and G to be whatever I want. Let's say I've got an arrow H going from C to A times B. Any H going from C to A times B. Then I can form H followed by first. And I can form H followed by second. And then H satisfies the following properties, trivially, right? If you go this way or you go this way, you get the same thing, because they were defined to be the same thing. If you go this way or you go this way, you get the same thing, because they were defined to be the same thing. So, right, we know H first followed by H second exists. We know H exists. We know they both satisfy the same properties, so because it's unique, they must be equal. Wow, wait, what's that telling us? Any H going from C to a product can be rewritten as H first followed by H second. Oh, let's see. What that's telling me is if I do H and extract the first component and use that as the first component of the pair, and I do H and extract the second component and use that as the second component of the pair, oh, that's just the same as doing H. Right? So it says doing H, deconstructing it into two components, putting those back into the pair is just the same as doing H. Right? And then one thing you could do is pick H to be the identity, and this tells you that taking a pair, extracting its first and second component, putting them back together to build a pair is just the identity. Leave the pair unchanged. Does everybody follow that? And then here's an exercise for those among you who are really keen. What you can do is, right, this is the definition of product. And this is anything that works this way is a product. Notice that there will be at least one other thing that works this way, which is B times A. And instead of first here, we use second, and instead of second, we use first. That's another thing that makes the diagram commute. There may be more than one definition of product. There might be an infinite number, even, of definitions of product, depending on what you're doing. That's okay. You can use what I've shown you so far to prove that any two products are isomorphic. Right? A times B is not the same as B times A, but there's an isomorphism which is just flipping the elements back and forth. You can convert one to the other and back easily. And all of these structures will have the property that they are unique up to isomorphism. And this is one of the lessons of category theory, is that you don't care too much about particular structures, but you do care up to isomorphism. So any two things that are easy to map back and forth, you can consider in some sense as being the same. Right? And this is true, right? If somebody said, you know, oh, I've got a product here. It's got a first field and a second field. And somebody else says, oh, I've got a different product over here. Mine is much better. It starts with the second field and then has the first field. You go, no, I don't think that's much better. I think that's equivalent. And now you can use a big word. Right? If one of your colleagues comes in and says, oh, I think we should just flip these things around, and then it'll be much better, you can say, oh, it's just isomorphic. Okay. Right? And why do we call it the product? Well, let's say that our object A actually has three values in it. Let's call them A, B, and C. And let's say that our object B has two things in it. Let's call them 0 and 1. How many things are there in the product? Well, it's all possible pairs. So it's A paired with 0, and B paired with 0, and C paired with 0, and A paired with 1, and B paired with 1, go away, and C paired with 1. So there's a total of 6 things, right? And in general, if you have some number in the first set A and some number in your second set B, and you take their product, it will indeed have the product of those two numbers of things in the final set. So that's why it's called the product. Any questions about that? Uh-oh, the questions have quieted down. Okay, think of good questions. I'm sure you'll have some. So, oh, and we'll need this construct later. There's another construct, F times G, and that goes from a product to a product. So we say let F be an arrow from A to C, and G be an arrow from B to D. Then F times G is an arrow from A times B to C times D. And we can build that up using the structure we've got. In fact, it's first on this followed by F, right? So first gives us an A, and then F gives us a C. And similarly, second gives us a B, and then we do G, and that gives us a D. So first F followed by second G, using the angle bracket construction. That just basically says, given a pair, apply F to the first component and G to the second component to get a new pair. And that's just saying this diagram commutes. So we've already got enough structure to apply functions separately to each of the two components of a pair. Not if you're going, yes, I'm bored, that's easy. Okay. Not if you're going, ooh, I can just barely follow that. Nobody's nodding. Not if you're thinking, oh, that's kind of cool, I'll go back and look at that later, I bet it'll make sense later, but right now I'm panicked and I don't follow it. So I expect there are people in all three classes. Okay, but the point is, yes, question. Oh, very good question. Why are some of the arrows dotted? So a dotted arrow in category theory is just a convention that means this thing exists and is unique. All the other structure here is enough to imply that this structure exists and is unique. Right, so the question was, so does this mean that we sort of assume the solid arrows all exist, and then from the solid arrows existing, we can deduce that the dotted arrow exists? And that's exactly right. Good question. And you might think, right, that this dotted thing is an absolute solid convention and that it always has a precise meaning. But no, you actually sort of have to write the precise meaning out later. Sometimes the dots can be a little bit ambiguous. But I hope that when I add some words to explain it, that stops being ambiguous. There was another question. Yes? Oh, right. So the question is, this is called a product. This is called a product. Is this called a product too? Yes. Yeah, everything's just overloaded. Yes. Okay. So a dotted arrow, we say this means it exists and is unique. What about the solid arrows? What does that mean? No, they're not necessarily unique. They're right. If we go back, right, there are lots of different Fs that you might use here, and lots of different Cs. So they're not necessarily unique, and they don't even necessarily exist, right? As we said, this is for all C. Maybe there are no C that satisfy this property. That would be okay. So dotted arrows exist and are unique. Solid arrows, if you happen to have one, then you can use it. Good question. Thank you. No, it's good question. So the question is the bottom line, if it exists, then it is unique? No, the bottom line is it does exist and it is unique. So it's quite powerful. It says this thing exists. We are creating new stuff out of nothingness. It's like being God. Yeah. F or G may not be unique. We're just saying, give me an F, give me a G that satisfy this property. Sorry? Can I list an example of when it's not unique? Yeah, let's try something. So let's take C to be the type bool. And let's take A to be the type bool. And let's take B to be the type bool. Okay, can you name me an F that goes from C to A? The identity. And we could take G to be the identity. And then we've got, this will give us the pair of that bool. So this takes a single bool into that bool copied twice. Okay, so it takes true into the pair true, true, and false into the pair false, false. So that's a choice of F and G. Can you pick a different F? Negation. So that would take true to false and false to true. Let's pick G to also be negation. And so now the product would be the thing that takes true to false, false, and false to true, true. And you could also pick one of these to be the identity and one to be the negation. Okay? So that's 4 different possibilities right there. And now, if you want to pick this to be the set of natural numbers, and the set of natural numbers, and the set of natural numbers, I bet you can think of lots of F's and lots of G's that you could use. Okay? Good question. I'm not going to ask John because he already knows the answer. Yes? Oh, very good question. Are there things that are almost products but not quite? And the answer is yes. For instance, pairing in something like standard ML is not quite a product because it doesn't work right with non-terminating programs. If either bit doesn't terminate, the whole thing doesn't terminate. So in the case that H was in, let's say F is something that let's go back to our example, right? So we mentioned 2 possible arrows going from C to A, the identity and negation. In a programming language, you'd have another possible arrow, the program that never terminates. Okay, so now we've got the, let this be the identity and let this be the program that never terminates. Now, have we got this right? So then when we build up a pair, what do we get? Oh, it doesn't terminate because this one doesn't terminate. So we don't have the property that H followed by first is the identity in that case because it doesn't terminate. So it's almost a product except for things that don't terminate. And the fancy word for that in category theory is, shit, I bet there is one, but I don't know the name for that. Okay, so you've already pushed me to my limits because I can't remember the name for that concept, if there is one. John, you get to ask your question after all. Yeah. Right, so John's pointing out that I've done a crap job here. I've done the same crap job that all category theorists do, which is when you look at this, first and second look the same as F and G, but that's not quite true, right? As I tried to make clear with words, but is not made clear in the diagram, first and second and A times and B and A times B are all fixed for a given A and B, whereas C can vary and you can have any C you like. Thank you, John. Good comment. Yes? Does this mean first and second are unique? Ooh, no. As long as you have A first and A second that work, that's allowed. And then can you prove that first and second are unique? I think you can. Good point. Given 2 different first and seconds that work, can you then prove that they're the same? And I think the answer is you can, but I can't do that off the top of my head. So I will leave that as an exercise for you. But I believe you can prove that first and second must be unique. If you've got another first that satisfies the same properties, it must be the same as the first. Good question. Excellent. Yeah. This one. Right. So you're pointing out this is called first and this is called first, but they're different arrows. So we've overloaded the name first. First is the name for the thing that projects out the first component of the product. And here first is again the name for the thing that projects out the first component of the product. But strictly speaking, this should be written first sub AB, and this should be written first sub CD. So we're using a bit of overloading. most people who use computers are familiar with overloading. So I've just simplified the notation in that way. But you're absolutely right. To be technically correct, this should be first sub AB, and this should be first sub CD. So that was a very good question. Okay. Last question, then we'll move on to sums. Yes. Can you have a thing that combines only some stuff? Yes, but it's not a product. How is it called? Well, it depends on what you're doing. I would call it Fred. I think you have a specific thing in mind, but I don't know which thing you have in mind. You don't have a product. Okay, so let's implement this in Java, right? So we'll have a class product AB. It has an A field called, a field of type A called first, and a field of type B called second, and we'll make them private. And then the product constructor just initializes both of those. And then we have two operations following Java conventions called get first and get second that retrieve those fields. So the things that correspond to the first and second arrows here are the functions get first and get second. Right, so this is clearly, right, this is already, for me, harder than the category theory, because now I have to understand classes and generic types in Java and so on. But for those of you that understand such things, are you happy with that as a definition of a product? And then we could use a product, right? We could make the product of the types integer and string. So we could make a new product with the integer 1 and the string quote 2. And then we could extract things, right? Get first gets out 1, and get second takes out 2. Okay? And the way you do it in Haskell is we'd say we form the product of A and B, and I'll use the record notation for Haskell. So we've got a pair whose first component is A and whose second component is B. And that's equivalent to just saying I built a pair of an A and a B, and then first extracts the first component of the pair, and second extracts the second component of the pair. And I could build a pair by saying pair of 1 and 2, and I could extract the first component by saying first of pair, and the other one by saying second of pair. Okay? Sums. We are now ready for our second data structure, the sum. So here's a diagram. And again, following John's convention, these bits are work for a given A and B, and then this is for any C. So given an A and a B, I say there exists an object A plus B, there exists an arrow left going from A into A plus B, and an arrow right going from B into A plus B. So left is the arrow on the left, which points to the right, and right is the arrow on the right, which points to the left. And then we're saying, okay, given any arrow F from A to C, and any arrow G from B to C, there's an arrow, now we use square rather than angle brackets, square F comma G close square, that exists and is unique. And again, that means that these equations are followed. And again, that means that, what does it mean to be unique? Well, it means that if left followed by H is the same as F, and right followed by H is the same as G, then H and FG satisfy exactly the same properties, and they must be identical. So we're given FG exists, and for any H that makes this thing commute, we know H must be the same as FG. And similarly, we can then do a proof showing that H is the same as left followed by H combined with right followed by H. This is the same proof we did before. And why is it called the sum? Well, right, how many people understand what the intuitive interpretation of this is? Okay, quite a few of you, a bit fewer, it's a little bit harder. So this is what we sometimes call the disjoint union, or sum is another name for it. And it just says, what is a value of this type? Well, it either says, I'm a left thingy, and then it consists of an A, or it says, I'm a right thingy, and it consists of a B. And let's do an example. So here, what's the sum of 3 and 2? Well, 3, remember, contained A, B, or C. So the values of this type are either I'm a left thingy, followed by A, B, or C, or I'm a right thingy, followed by 0 or 1. So that's called this sum or disjoint union. Does anybody else have a favorite name for this? I think there's several different names for this. Yep. Discriminated union, yeah. Either is what's called in Haskell, indeed. In Pascal, I think it's called a record variant. That's another name for it. What's it called in C? I can't remember. Union. And in C, it's called union. So everybody else is discriminating, and C is not. And, oh, I was missing an equation on the other one. Yeah, I skipped over something. Right. There's one other thing that's very important that I should tell you about products, which is, what is the product telling us? Well, it says that the arrows from C into A times B, right, the only way to build such an arrow, right, is the only arrows that exist are those arrows that you can build by taking an F paired with a G. Wait, how do I know that? How do I know that any possible arrow is one of these? Well, remember, we proved that. Here's any H going from C to A times B. That H must make this commute, must make this commute. Therefore, this H must be equal to H first followed by H second. So any possible arrow going from C to A times B must be expressible as a pair. This proves that, right? You get a lot from very little structure. So in particular, what does that tell us? It says, what is the set of arrows going from C to A times B? Well, it's in one-to-one correspondence, right? Because you can build an FG with the arrows from C to A and the arrows from C to B. So a different way of thinking of all this at a some higher level is look, so curly C there in black just stands, curly C is the name of our category. This stands for the set of all arrows from C to A times B. And it says, that set of arrows is in one-to-one correspondence, in isomorphism with the set of arrows from C to A and from C to B. So it says, if you want to know about an arrow from C to A times B, you can break that up into saying, I've got an arrow from C to A, that gives me the first component, and an arrow from C to B, that gives me the second component. Or it says, given these two things, I can build such an arrow. This is a very compact way of describing products. It says the arrows from C to A times B are in one-to-one correspondence with, or in isomorphism with, a pair of arrows, one from C to A and one from C to B. And when you learn more category theory, you learn that this thing here is also a product in the category of categories. Yee! We won't worry about that, but it's true. Okay, so, and then similarly, right, what we learned for sums is just the same thing. It says an arrow from A plus B into C is the same as having an arrow from A to C and an arrow from B to C. Oh, right, and what is this arrow? Right, this is like a case expression. Right, it says, look at this thing. If it's a left thing, apply F to it. If it's a right thing, apply G to it. So it's just a case expression. And again, it says the arrows from A plus B to C consists of a pair of arrows, one from A to C and one from B to C? Yeah, very good question. Exactly what I was going to point out. Right? People look at this and go, wait, times? No, shouldn't it be plus this time? No, it's still times. Right? Because we've got a pair of things. It's not a choice. It's not the arrows from A plus B to C are given by having either an arrow from A or an arrow from B. No, you need both, one for each case. So it's times, not plus. Very good question. Yeah. Yep. Right, so in algebra, this is called the sum of two algebras. This is a concept that already existed in algebra before category theory came along. And then category theory captured that in a very nice way. Sorry, what you're asking what the operators of the algebra are? Right, so algebras may have any number of operators. They might have one operator or two or three, and they might, so you don't always have plus or times. You can have lots of different things in your algebra. But if you had plus and times, what this would be saying is that left preserves those, and FG preserves those, and F preserves those. So that's giving you very strong properties about the sum of two algebras. Okay. And then we can implement sums in Java. All we need to do is use a smaller font, right? Because sums in Java are significantly more complicated than products. So we need to define an interface sum, and that's going to have a case expression, which says, well, give me a function f from A to C and a function g from B to C, and I'll return, and given a sum of A and B, I'll return a C. And then we define two instances of that interface, the left instance and the right instance. And the left instance has a private field of type A containing an X, and the right field has a private field of type B containing a Y. And left and right are the two constructors for this type, right? For pairs, we just had one constructor. For sums, we have two constructors. Either it's an A on the left or it's a B on the right. And then the case expression for something on the left just picks out the F and applies it to X. But the case expression for something on the right picks out the G and applies it to Y. And you need to provide both a pair of things, F and G, so that you can do something whether you're given something on the left or you're given something on the right. Are there any questions about that? Any criticisms of my Java programming style? Okay. And then we can use that. Again, we need a smaller font. So we'll define arint as a sum of a string and an integer. So the idea is this is either an integer or an error message. And so we could find error as left of error, something went wrong, or one as right of one. And then we can define a function, add, that takes an arint called this and another arint called that and adds them together. And what will we do? Well, we have a choice. We have to look either at the first argument or the second argument. Let's look at the first argument. Either it's an error, and if it is, we'll just return that error, or it's a number m, and in that case, let's look at that, and either it will be an error, and then we just return the error, or it will be a number, and then we add the two numbers together and return that. So this just takes two things that are either errors or numbers. If they're numbers, it adds them together and gives you a number. If one of them is an error, it will give you an error. Is that, yeah? Sorry, interfaces and polymorphism are, speak up. Interfaces and polymorphism are sums in category theory. No polymorphism you would actually model using a generalized product. Polymorphism says you get one of these for any possible type. We can deal with that one offline if you want. And interfaces are what is the nice categorical interpretation of object-oriented programming? No one knows. Maybe there isn't one. What is the lesson I derive from this? Object-oriented programming is very well named. When somebody tells you they want to use object-oriented programming, they're telling you what you should do. Object! We've got very little time left, so let me rush on. Sums in Haskell are very easy. It's a type, I wrote sum here, but it's actually called either in Haskell. I think, are the constructors called left and right, or are they called inal and inner? I can't remember. Sorry? They are called left and right, so I should have written that as either. And then we can do the errand program the same way, except now we can write it in a big font. I'll put all this up on my website if you want to look at the slides in more detail. Exponentials, the third important data structure. So now we're building on top of products, which we've already done. So I'm saying, given an arrow f going from c times, oh, this one's hard, by the way. This one made my head hurt really a lot the first time I learned it. It's like, what? You're just defining functions and you need products and it's about currying and boy, category theory is just about taking something simple and making it difficult, isn't it? But this is the easiest way of doing it just with the structures we've got. So this is what we'll do. So it says, given an arrow f from c times a to b, there exists a unique, so this should be a dotted line, except the ID isn't a dotted line, so I drew it solid, but maybe I should have drawn it dotted. See, I told you it was hard. And what are we saying? There exists a, so we say this is like first and second. So for any a and b, there exists an exponential from a to b. If you take the product of that with a, there's an arrow app that goes to b. And then we're saying there exists a unique curry of f, such the curry of f cross ID. So curry of f takes your c to an a to b, ID takes your a to the same a, and then we're saying this is the same as this. What's going on there? Okay, this is a function space. It's, right, arrows go between objects. This is an object that represents the arrows between A and B. So we've turned arrows into objects. Ooh, it's almost like turning code into data. Ah, okay, we can live with that. We're computer scientists. We know how to do that. So this is the set of all functions from A to B, in a sense. It's the object that represents all the possible arrows between A and B. And then given one of these and given an A, what can we do? Oh, you apply the function to the A, and that gives you a B. So that's what app is. It's just applying a function to an argument. And then why does this diagram commute? Well, I'm saying, okay, I've got F that takes two things, a C and an A. I'm turning it, that C, into a function from A to B. So that's something that takes an A, and I give it an A, and I get back a B. So it says, okay, instead of representing something from a pair to this, we'll represent it as something that acts on the first component of the pair, gives you the second function from the second component of the pair, and then we can apply that. So this is a trick for representing functions of two arguments in terms of a function of one argument, curry f, that gives you A to B, a function on the second argument. So this idea goes back to Haskell Curry, which is why it's called currying. Actually goes back a bit earlier than him to Moses Schoenfinkel. So it should be called Schoenfinkeling, but that's less tasty. But actually, so that's the joke I was told when I was a student. Much later I learned, actually it goes back to Gottlob Frege, noted inventor of logic and anti-Semite, sadly. It turns out basically that lots of the people who are really good at logic are anti-Semites or Nazis. That's not a recommendation in favor of anti-Semites or Nazis. But anyhow, so this idea of currying goes back to Frege, so we should call it frigging. So that's an exponential. And this is the equation that we get. It's a little bit hard. Why are they called exponentials? Oh, well, if I've got a function from a set of 2 objects, 2 set of 3 objects, how many are there? Well, 0 could map to A and 1 could map to A, or 0 could map to A or 1 could map to B, or 0 could map to A and 1 could map to C, and so on. And you can see that there are 3 squared, 9 different possible such functions. So the number of such functions just given by raising the range type, the number of elements in the range, to the power of the number of elements in the domain. So we flip things about and take the exponential. So that's why it's called an exponential. Okay, so now we know our 3 basic functions, right? We've got O, and we can do all this. Oh, right, and then what's that telling us? It says, well, the functions from C into A arrow B are in one-to-one correspondence with the function from C times A into B. That's the important isomorphism that this is capturing. And then Java now contains exponentials, so we can go back to using a large font, right? Because the function type is built into Java now. And it's, of course, built into Haskell as well. So it's all very straightforward. So here's an example of currying, right? Add takes an integer and returns a function from integers to integers. So it takes the function that given x adds n and x. And so add1 is the increment function of type int to int, and then increment applied to 2 gives us 3. Fair enough? I mentioned at the beginning simplicity in Michelson. I'm running out of time, but here's the complete type system of Michelson. And this line, and this line, and this line are giving you the definitions of sum, right? This is left, this is right, and this is your case. And that's the complete type system of simplicity. It really is very simple. That's the complete semantics with these 4 lines here, just saying inject left is, that's their way of writing left, inject right, that's their way of right, and case is, it does a case branch, right? So if it's the left of A, you apply to A, you apply S to A and C, and if it's a right of B, then you pick out T and apply that to the B and the C. And Michelson also has sums built into it. So here's a little bit of the Michelson documentation, which is about 20 pages. It's much less simple than simplicity. But again, they have sums built right into it called OR. And Plutus, let me mention about Plutus. So I mentioned I'm a consultant for IOHK. We're designing our own smart contract language called Plutus. Anybody who's looked at cryptocurrency will know of exploits like the DAO reentrancy exploit, which lets somebody steal $30 million US from investors. And that sounds pretty bad if you can have an error in your code that lets people steal millions of dollars worth of stuff. But that's not the real story. The real story is there have been similar exploits about once every 6 months. And one of the things at IOHK that they're intending doing is providing a drop-in copy of Ethereum. So I keep reminding the CEO, Charles Hoskinson, who's an amazing fellow. I keep saying, okay, so what you're saying is you want to maintain the ability to have an exploit every 6 months. So that's the bit that's duplicating Ethereum, but we're not just going to duplicate Ethereum. We're going to have our own smart contract language called Plutus. And the hard part here is, how do you design it so that these very clever errors, so some of the errors that have let tens of millions of dollars been sold are really stupid. You just look at that and you go, oh, the problem is they were using object-oriented programming with delegation. Don't do that. That's easy to avoid. And that one cost another $30 million. But the DAO reentrancy bug is really very fiendish. So how do we avoid these fiendish bugs? Let's apply category theory. How do we do that? That's an open question. Do you want to help us do that? We are hiring. So we're hiring 6 programming language engineers for the Plutus team. There's a long URL here at the bottom. As I say, I'll post this on my website so you can find it there. But the easy thing is to enter your favorite search engine, type IOHK is hiring 6 programming language engineers, and you will find it. So please apply. If you're good, please apply. If you think you're not good, please apply anyway, because you're probably good, right? If you think you're not good, you're probably not male, and we want you to apply. Conclusions. Right? 2 cool things I want to show you. The first is, right, when you look at the sum diagram, it probably looked a lot like the product diagram, right? You're going, oh, there's something similar there. I wonder what it is. And what it is if you look at it, right, the diagrams are exactly the same, except instead of an arrow out from A times B to A, we have an arrow in. Instead of an arrow out from A times B to B called second, we have an arrow in. And instead of an arrow out from C to A and an arrow out from C to B, we have arrows from A and B into C. And then instead of an arrow from C to A times B, we get an arrow from A plus B to C. So you just turn around all the arrows. So there's a very close relationship between these 2 things. And I never would have seen that without category theory. Right? This is the real advantage of category theory. And right, we've already seen a benefit from that, right? The second set of proofs for sums I went over very quickly. That's because since all the arrows are just turned around, it follows automatically from things being true for products. So every theorem about products turns into, by just turning the arrows around, into a theorem about sums. So this is very cool. And what does this mean, right? I'm waiting for somebody to exploit this. It should mean that you have a compiler for a language that just has products, and from it you can automatically derive, by just flipping all the arrows, a compiler for a language with sums. There's actually been a little bit of work along those lines, but someday somebody will reduce the size of their compiler by a factor of 2 by using this trick. And here's the other cool thing. You haven't learned anything new today at all. You knew all of this back in high school. Let me prove it to you. Right? What were the 3 things that summarized all this? It said that the set of arrows from C to A times B is in 1-to-1 correspondence with arrows from C to A and C to B. Arrows from A plus B to C are in 1-to-1 correspondence with arrows from A to C and B to C. And arrows from C into the exponential of A and B are in 1-to-1 correspondence with the arrows from C times A into B. Notice that these themselves stand for sets of possible arrows, so these are essentially like exponentials. Let's just write them as exponentials. And then that tells us A plus B to the C is the same, that's right, the set of all arrows from C into A times B, is the same as the C to A times C to B. In other words, A times B raised to the C is the same as A to the C times B to the C. You learned that in high school. C to the A plus B, all the arrows from A plus B into C, is in 1-to-1 correspondence with arrows from A to C and B to C. In other words, C to the A plus B is C to the A times C to the B. And B raised to the A, and that itself raised to the C. So here we've got the exponential of A to B, and here we have all the arrows from C into that. So we've squished 2 different kinds of exponentials, writing them the same way, are in 1-to-1 correspondence with the arrows from C times A to B. Silent awe. Perfect. I will put this on my website. There's some further reading for you. I'm sorry that I've gone over time, so I will finish now, but I will leave you with just one idea, which is you should think that when you have a tough job to do, this is a job for mathematics. This is a job for lambda calculus. I'm going to do something non-PC.